Uh, Hello, am I audible?
Yes, yes, yes. Continue, Manas.
Okay. Okay. So the modification that has been incorporated for this optimization of composites is basically in the regular steps. We have initial population, then fitness evaluation of those population, and followed by the fundamental steps of mutation and crossover. But in this modification, what we have done is we have incorporated a check. A check is in the form of a while loop, and unless a particular lamina is balanced, we will not let it go to the next steps. Next step is generation of trial vectors, and then fitness evaluation, then selection. All the steps will not be carried out unless these two steps will resulting in offsprings which are balanced. So this step is introduced by a function and a while loop, which I'll be subsequent slide. I have shown the details of that also, so that interested people can see that. I have already given this slides to Ajit. They can refer that also. So the similar modification can also be introduced in genetic algorithm. Uh, the after crossover and mutation, similar while loops can be introduced, which will do a check of the offspring, and if they are not balanced, the process will be repeated then and there. Uh, and how it increases the speed of the assessment is because the most time-taking step among this is the evaluation. Evaluation will only be taking place only when the offsprings are meeting the requirement. The constraints are pre-fed and pre-tested. In the conventional method, how it works is constraints are put on the evaluation step. After the evaluation, if the if the constraints are being met, then some kind of bonus is added. If the constraints are not met, then some penalty is added to the evaluation, the fitness in the evaluation step. But since I mean this step, this method of doing the implementation of the constraint is proven to be time consuming because evaluation is the most time consuming step. So we should first check the constraint without actually evaluating these constraints, this balanced constraint and the symmetric constraint. And the evaluation should be taken place only for the constraint for the population which is satisfying all these constraints. So this is how the time aspect of it is playing a role. I try to give a glimpse, and further we will see on this. So this box shows a code which is written in Python to show uh, if a particular laminate, which will be represented by an array in PP, just given a name, um, if it is balanced or not. So before going to this code, I will just explain. We have considered the angles from 90 to 0 degree at an interval of 15 degree. So like 0 degree is given a code name of 1, 15 degree is given a code name of 2. Similarly, minus 15 is given a code name of 3, so on and so forth till 12. There is no minus 90, no minus 0 because they are like same as 0 and 90. So once this coding is done, the laminates, like suppose we have a laminate of 15 degree, 45 degree, minus 15, minus 40, it will be represented by 2637 and S, okay, symmetry. So this similarly the other 16 if the laminate contains 16 lamina, laminae is one layer. When 16 layer we consider them together, it is called laminate. So we represent this big laminae in the form of 8, 9, 12. Like this, there is a code. So this is how this first coding is done, and then after the coding is done, it will be this code will be passed to this function where it will check if the mechanism of checking is explained here, that it will see if the laminate is balanced or not. If it is balanced, then it will take it to further. And in the previous slide, as I was telling, there are some more codes involved where which all I have not shown because it will be too lengthy. Where these loops are also involved, uh, coded so that it will check if the particular population is meeting the criteria, and then the offspring is meeting the criteria or not. If it is not meeting, then some process has to be repeated. Okay. So this is the parameter optimization. Now, first validation of this method I will be doing with considering a cylinder which will be subjected to external pressure. Such cases find a real life application where a structure is subjected to mm, subject is submerged in the ocean. So such structure which is subject to external pressure is finding application in structure which are submerged in the ocean. So they are subjected to high pressure, external pressure. So there was a tragic accident of Ocean Gate. We have known that 1 or 2 years ago, and similarly there is a launch. Samudrayan, as a vessel which is being developed in a collaboration with NIOT and ISRO. They have developed this vehicle for going into the. So this is with these pictures. I just want to say that this kind of load case has got a practical application also. And in order to estimate the failure load, in order to evaluate, as I was telling, that evaluation is the most time-consuming step. There are two methods. One is analytical methods, as given in a standard document is NASA SP 8007. There are few more equations which are calculated based on the ABD matrix of a laminate, which gives the critical buckling pressure for a cylinder subjected to external pressure. And similar calculation can be done with FEM, finite element analysis, but the code can be written by suitably coupling, and this coupling of FEM analysis with Python has already been shown in the fracture section, how a journal file can be linked, can be referred in this presentation itself. Not only journal file, input file can also be run with Abacus, that I'll be showing in subsequent slides also for a different application. In this slide, I am showing there is a comparison between the optimization carried by Chun and Guang. They have taken a baseline design which was made by Moon et al. They have designed a cylinder subject to external pressure, and the values which were obtained by them is shown in this table. And as we see, there is a tremendous improvement in the buckling load of the order of 30 to 35%. And this has been verified. This analytical method is the one which I was showing, this NASA code. And FEM, as we know, this FE analysis. So we see that even though they are not exactly matching 1:1, analytical and FE, but okay, the increase is of the same order. And the optimization carried by Chun and Guang suggested this layer, which is plus minus 90 and plus minus 85, 10 and 12. Okay, this is the laminate. As we see that plus and minus are together. As I was telling, that this is an unnecessary constraint. But the suggested layer by this algorithm is 30. We can see that there is 30 and there is minus 30 and there is a 90 between them. So this is what I was trying to bring out there, that the two lamina which are balancing each other need not be together. They can be separate. So that is the thing. And still the overall laminate is balanced in a overall sense. And this graph is made so as to monitor the optimization during the progress. So once all the three curves converge to each other, we can consider that the optimization has taken place. Similar comparison is done with other literatures also. Other researchers who have carried out the optimization for similar load case where the cylinder is considered and the optimization is carried out with respect to the cylinder subjected to external pressure. And we have seen that improvement in all the cases with the proposed algorithm. The algorithm in Haj Mohammed et al., this case, we are able to almost replicate the one which was suggested by them, their optimization. So it validates the optimization process. Then when we compare the optimization with respect to V et al. With their paper, we find that in terms of buckling load, there is not much improvement. The layup just suggested by them is not a balanced one as it is suggested, but the layup suggested by this algorithm is balanced, symmetric, and at par with the load. In fact, it is still slightly higher also. So, but the most important thing which is to be noted from this table is the time taken. Time is also mentioned in their paper, and computer, this hardware, obviously, it is of the comparable level. We have run this software, run this algorithm on a comparable hardware. And we see that they are there is a tremendous reduction in the time taken. But since this hardware, this proposed algorithm's one merit that it takes less time computationally is proven with this. But the second merit is that this algorithm can be tweaked so as to introduce the geometric variable as a variable also along with the layup angles. So layup angle is a variable which defines some codes, and it is represented in terms of array. In the same array, if we add another number at the end and we say that this number will represent the geometric value of certain parameter. So in this case, diameter is added as a variable and it is allowed to vary from 800 mm to 1200 mm. Originally, the diameter of the cylinder which was designed by V et al. Was 1000 mm and it was having 50 plies. So we kept 50 plies. We kept the volume as 1 meter and the length as 2 meter, and the calculated volume we kept it as constant as 1.57 billion mm cube. But we allowed the diameter as to behave as a variable, and we defined the design space as 800 mm to 1200 mm. With that, when we modified this modification and carry out the optimization, we find that the optimum diameter should be 981 instead of 1000. And the buckling load for that case, even though the volume is constant, the buckling load will be 28.98, which is 8.5% higher than the values suggested by V et al. So this is how we can still get a higher value and in a very one third or one fourth time. So such code can also be modified to any software. This algorithm can be incorporated in any software which supports scripting. One of our in-house software, that is Feast, finite element analysis for structures. It stands for Feast. This is a software developed by ISRO, and we have it supports Python scripting, and we have done one optimization where the stiffeners, the number of stiffeners is a variable, and uh, the shape, overall shape, the size of the stiffener is another variable. So we find that after the optimization is that number of optimization is instead of 36, which was in the original design, it should be reduced. It should be increased to 48, but the overall size is to be reduced. So doing this, we have reduced the mass actually. So we have reduced the mass while fulfilling all the design requirement of strength and stiffness. So this, having said that, I'm going to uh, talk about how this algorithm can be made further fast and further improved. So this further computational improvement can be done by introducing a surrogate model. So surrogate model is uh, a model which will be developed based on the data rather than based on the physics of the system. So in this case, we used a neural network, and since it has got multiple layers, we call it as deep neural network. So we consider the initial design of a truss structure. So this intertank truss structure is having about 24 members, and the dimension of the members are given in this slide. It has got 28 layers of 0.1 mm lamina is the initial layer is given here, and our objective is to increase the buckling load without increasing the mass. The constraint is mass, so we have to play with the thickness alone, and obviously it has to be done in a very short time so that the concept of neural network is being added for this. So because this laminate is having 28 layers, this whole method is being demonstrated first with a smaller cylinder, smaller in terms of having lesser number of layers. So this concept has been demonstrated on a cylinder which was given on a research paper, where there is only 8 layers, and because of symmetry, there is only 4 design variables. So for that, a neural network was made with all the 10H activation functions, and it has got 4 input layer and 1 output layer. The output layer represent the critical buckling load. The hidden layers are having 20, 64, 32, 16, and 4 layers respectively. And training data based on the FEM is generated. It was validated with the values which were given in that research paper, as well as random values, so generated random laminate values, and then the FE based buckling load as well as the neural network based FE loads are neural network based buckling loads are calculated, and found that is, and the target was to have a error less than 5%, and we were able to achieve that with something around 300 data points were generated for the training purpose. Then the validation was carried out. Then subsequently it was used for optimization, and with the optimization we found that 196 kilonewton is the buckling load with this layup which was suggested by the paper by this algorithm. 15 minus 60, 60 minus 50 symmetry. And the paper was having the cylinder which they have fabricated is 0 plus minus 45 0. So this is how this kind of optimization has been can be done. And with that validation, this optimization of this truss structure was finally carried out, which is having 28 layers. And because of symmetry, 14 design variables are there in this case. And because of 14 design variables, because the number is higher, so we have considered 1,000 data points as the design as the training data. So as to keep the error within the set benchmark of 5%. So with that, when we did the optimization, we could increase the buckling load to 441.7 kilonewton, which is around 12.9% higher than the initial buckling load of 392 kilonewton. And here is a comparison of if we are not doing the such modification in the algorithm, if we do a generic, because in Python as well as in MATLAB, uh, there are ready-made functions for doing genetic algorithm or differential evolution based optimization. But such algorithm or such functions will not give us the freedom to tweak the in between steps. And if we do with this optimization with that functions, we'll not be able to get a converged solution even with a high population, even with a higher number of generation. This is being shown with this slide. And this is a summary of the observation with the which we have carried out with the smaller cylinder, which is having only 8 layers, that is 4 design variables. It is shown that the initial buckling load of 165 was increased to 168 only with the conventional algorithm, where there is no modification in the algorithm. It is able to increase only by 3 or 4 kilonewton. But if we do the modification with a very short time, we are able to get a very high buckling load. So the next part of the presentation, I am going to talk about the optimization of composite structure. So sandwich composite structure. Here there is a core, and there are laminates which are acting as a face sheets, both on both the sides of the um, core. So here the thing is, both are okay. Earlier we used to have a array which used to represent the design variable that used to represent the angles only. But now here, the novelty of this work is we have introduced the number of lamina and the core thickness as also as a design variable. So if we have to design a structure, how many layers are to be there and what should be the core thickness? I mean, these answers will also be given by the optimization, the algorithm. No need to pre-decide any variable. We just have to give the dimension and the material properties, and the optimization algorithm will tell us what is going to be the actual configuration. So this novel method of optimization of sandwich composite structure is validated with the optimization carried out by one research paper. The author name is Lee et al. They have actually they have used the cylinder which was originally fabricated by Kim et al. So they have fabricated and tested, and subsequently Lee et al. Have optimized that cylinder and shown that some other layer other than the one which was used for fabrication is actually better. Now we have validated this our algorithm with respect to their result, Lee et al. We found that the results can still be improved. The details of the cylinder is given, the geometric features and the number of layers, layer thickness. The phase sheet was 094s, while for the original cylinder. And this is the code. One more thing which I forgot to tell is that the failure criteria or assessment for this cylinder is carried out based on two methods. One is the strength-based failure. The other one is buckling-based failure. So here is a snippet of the codes which were used for only the buckling aspect. So here I have shown that since the overall geometry is not changing, it's only the layer which is changing, the number of layers, the core thickness, which are represented in terms of the layer. So even the input file can be used for making running this code. So the input file is first divided into two parts. Uh, for example, in this case, for this case, as I said, there are two assessment methods. The one is the structural analysis, another one is the buckling analysis. For structural analysis, we have to run static analysis, which will be a separate input file, and this buckling analysis will be a separate input file. So this representation I have shown for the buckling analysis, and in this buckling analysis, we have to first separate the or break the buckling that input file into two pieces, LBS1 and LBS2, from where we have to break it from the line where it is representing the layer, and after that we have to write the layer according to the variable which is represented by the B. B is that variable which will represent what are the angles, and the core thickness will represent the core thickness, and this is how the input file will be changed every time as the iteration or the optimization will progress. Eigenvalue will be read subsequent to this working analysis, and similar analysis will be carried out for the static structural analysis, and in that case the stresses in the various layers in the principal direction will be read, and they will be compared with the strength. This is the snippet to show how the iteration are progressed for the different steps of the differential evolution algorithm. Okay, the results are compared in this slide. We saw that mm, the proposed algorithm is able to give better buckling load for most of the cases which were considered by Lee et al. The original cylinder was fabricated only for the core thickness of 12.5, but Lee et al. While they were doing the optimization, they have done the optimization for some other core thicknesses also. They have shown that for different core thickness, different layups are optimal. But what I find is that even though I mean, they are different, but the layup suggested by this layup is, this proposed algorithm is different, and they are found better, except for one case, that is when the core thickness is 30 mm. For that also, the investigation have done and found that there was a preconceived idea in that paper that this layup will be in this format, but the proposed algorithm does not require any preconception about what kind of layup is going to be. We just need to define the problem, and the algorithm itself will tell us what is going to be the best performing algorithm, layup. That is one thing. No preconceived idea required about the layup. The second thing is that uh, the as we know that these composites are very sensitive to the performance. Fabrication performance is deeply related to the fabrication. Any error, any shift from the actual fabrication angle, it may drastically affect the performance. So this is seen in this layup, which was suggested by and we find that the layup suggested by by the proposed algorithm is very less sensitive. If there is a change in the angle of different layers by 1 degree, 2 degree to 5 degree, this variation is incorporated, and we have seen that there is a very less reduction in the performance. And then the cylinder with different mass constraint were validated, and we find that there is a increase of the order of 35%. The buckling load has increased by 35% as compared to the optimization carried out by Lee et al. Similar comparison is made for the different masses also, and it was observed that the higher buckling load can even be attended even with the core thickness of 30 mm. So for that core thickness, where the core thickness was 30 mm, the code has suggested that the core thickness should be only 22, the number of layers should be 17, and the buckling load obtained is 8.50, which is slightly higher than the load suggested by that paper. And in addition to that, it is less computationally expensive. The number of steps involved in the computation is less, as well as the main thing is it is not sensitive to the fabrication process. Even if there is any error in the actual fabrication, there is an angular error in aligning the fibers. Still, the design is robust enough so as to not deviate from the intended function by a greater amount. So with this, I am concluding my talk on this topic, that I have covered the various material and the challenges, particularly with respect to managing steel. Because of its high strength, it is prone to fracture, and how the fracture assessment is carried out. The three parameter fracture model, which we are currently using for assessing the fracture of the various metallic motor cases. And this is uh, and the developments, how we are able to couple the FE analysis with respect to the fracture assessment in the three parameter fracture model. And the assessment, I mean the optimization of composite structures, how this optimization of composite structure can be done without any commercial software. um, so if we have one assessment method, evaluation method, we can couple it with a differential evolution or genetic algorithm, or for that matter any evolutionary algorithm. There are so many other algorithms also which I have not covered in this presentation. So they can also be covered with this. Similar modification can be done, like checks and loopings can be incorporated, so as to make them um, customized for the purpose of composite optimization. So with this, I would like to end this talk. If any doubt or any queries there, I would like to answer that.
Participant can ask the question, if any. They can unmute yourself. Any questions? Okay, I think there will be no questions. Uh, so thank you, Dr. Manas, for accepting our invitation and presenting a very informative, you can say, the session. So thank you, and we'll hope in future also we'll do some this type of work in future also. Thank you, Dr. Manas.
Thank you. So I'm leaving then.
Yes, yes, thank you. So participant, it is for the information that the assessment test will be starting from 6:30 for the 45 minutes. If you have any queries regarding that, you can ask. Regarding assessment test, if you have any queries, please ask.